Let's have a look at the different routing protocols. We have different ones and all of them are already available for IPv4, so you might probably know them. But let's start with the basics first. The routing table of IPv6 is generated like in IPv4. We have different information with the prefix, which you can also call the route, with the prefix length, that's the slash notation. We have a next hop, that's the gateway for this destination. We have a route source. So in the table, you have the protocol which the route comes from. You have a next hop interface, that's the outgoing interface where the next hop resides. And you have a metric that you can use if you have two of the same routes, but you want to prefer one, you can set a different metric. Let's start with the easiest protocol first, RIPng. RIP is Routing Information Protocol and NG is next generation. This was created for IPv6. It is a distance vector routing protocol. It is really slow in convergence and it's not a good thing, but still RIP is an open standard and is supported by all vendors. It uses a metric which is called cost, and this is the hop count. The maximum can be 16. The concept is equal to the RIP version 1 concept and the RIP version 2 concept for IPv4. There is not much difference. Let's look at some details. We have limitations like in IPv4. The network diameter can only be a maximum of 15 hops, which means you can only have a fairly small network and you don't want to use RIP really. The next problem is metric does not care about link speed. So if you have a 10 gig interface and you have a 100 meg interface, RIP does not know and it might carry your traffic over the 100 meg that is full, while the 10 gig is not used and everything will be slow. And like I told before, the convergence is really slow. Don't use RIP, it's not recommended. Better option is OSPF. We have OSPF version 3. This is a link state routing protocol and it supports IPv6 and IPv4. OSPF is also an open standard and is supported by all vendors. OSPF is really scalable, it is stable and it is proven in IPv4 and also in IPv6. Let's have a quick look at the difference between OSPF version 2 for IPv4 and OSPF version 3 for IPv6. We have different LSA types, you know that probably, and the router LSA and the network LSA and also the router ID, they stay 32 bits. So you cannot use an IPv6 address as your router ID. You have to use an IPv4 address. This could be a problem if you have an IPv6 only router. You have to manually set the router ID or else the OSPF process will not start. The processing of OSPF messages happens per link or per interface and not per subnet like in IPv4 because, like you know, a single link can contain multiple IPv6 networks. It's not like in IPv4, you only have one network per link. No, you can have multiple. So you have to do the processing per network. And you can also run multiple instances per link if you like. The communication in OSPF version 3 happens over the link local addresses per link, except for the virtual link, but that's a special thing that we don't have to go into detail. Authentication is the IPv6 integrated IPsec authentication header. It is not done in OSPF itself. The OSPF packets are encapsulated directly into IPv6. There is no more TCP or UDP. There is only a native IPv6 packet. That makes it more powerful. And if you have a header of a packet, then the next header field is set to 89 to indicate there is another header, which is an OSPF header. Let's have a look at the different LSA types. On the right, there is OSPF version 2 for IPv4, and on the left, there is OSPF version 3 for IPv6. Most of it is the same. We have two new LSAs, and we have one that's already deprecated again, that's the MOSPF, and it used to be group membership, but it's not used. If you're interested in this, you can read more about it. The third option is EIGRP for IPv6. This is also a link state routing protocol. It's similar to OSPF, but it's a Cisco proprietary standard, so you cannot use it on your HP device or on your other switch or other router. It's only Cisco. It is still stable, it is scalable, and it is proven, and it is widely used. There are some differences like in OSPF. The router ID also stays 32 bits, so you cannot set an IPv6 address as router ID. There is no auto summary anymore, because IPv6 is always classless. Remember, auto summary was used to summarize at the classful boundary, but we don't have classful addresses anymore. There is also no split horizon. Remember, split horizon means I am not sending out an advertisement to a neighbor which I received this advertisement from. Because interfaces can have multiple prefixes, it makes no sense. If I received a message on this one interface, why should I not send it out on the same interface? Because I could try to reach a neighbor that is different and on a different network, but reachable via the same interface. So no split horizon anymore. And in EIGRP for IPv6, you have to do an explicit no shutdown on the process or it will not start. Like with OSPF, the source address of the hello packet is the linked local address, and the target is a multicast group, all EIGRP routers. Updates are sent via unicast to the specific neighbor, so there is no broadcast, and there is also no multicast for updates. Authentication is done via MD5, IPsec in the future, but IPsec is not available yet. It's not implemented. The protocol that's used on the internet is BGP. It's my favorite routing protocol. The current version is still BGP4. This is a path vector routing protocol, and this is used on the internet. This is the big one. This BGP protocol is also commonly used in MPLS VPNs. There is a multi-protocol extension that enables IPv6. In BGP, we are doing configuration via different address families. We did that before. We use IPv4 unicast for IPv4. We can use IPv6 unicast for IPv6. Or we can use VPNv4 or VPNv6 for MPLS. It is recommended that you do separate peerings for IPv4 and IPv6. You could also exchange the different address families via the same peering. Like you have an IPv4 peering to your provider. This peering could also provide the IPv6 addresses, but this is not recommended. I will tell you in the next slide. Apart from that, BGP for IPv6 is functionally identical to IPv4. It's the same process, it's not any different. So why do we prefer separate peerings? With only one peering, you have to manually set the next hop because you get a message from your neighbor. Let's say the underlying protocol is IPv4 that you peer with your neighbor with. And the neighbor sends an IPv4 route. This route's next hop is automatically set to your peer's IP address, so you know where to send messages to this address to. But with IPv6 over IPv4, it cannot set its IPv4 address, and your router does not know the IPv6 address of the peer, so it does not make sense. You would have to manually set the next hop. And also, if you lose IPv4 connectivity somehow, IPv6 is also gone. So please configure separate peerings. It makes it more scalable, it makes it more reliable, and you don't have to set the next hop manually. The last routing protocol we're looking at is ISIS. It's also a link state routing protocol. It's very similar to OSPF because it uses the same Dijkstra algorithm, and it works on top of layer 2 instead of layer 3 as compared to the other protocols, and is thus protocol independent and was IPv6 capable without any modification. ISIS is commonly used with ISPs and also used with this shortest path bridging, a new replacement for spanning tree. We will also not go into detail. ISIS has supported IPv6 ever since. There was no modification necessary because it does not run on layer 3.